one of the things I want to kind of stress here beyond my talk and just about this program, especially to the students, the pre-careers, the early careers, and mid-careers too, and everyone here, is that this program here is extremely important. It's so important that these guys who are like instrumental in starting it, they're retired. They don't have to be here. They could be fishing, But they're here, and they're talking to us. So they were passionate about it. They're so passionate about this topic and this program that they worked on it in their career, but then they're here in their retirement. So I think that is a testament to how important this program is. So also with this program, it's been talked about a lot, is it's now providing us data to analyze fire, right? All of the talks, these science talks, really wouldn't be possible if there were no fire. If all these fires were put out, we couldn't study fire. So thanks to you guys, now I have a job because now I can study these fires. I would be unemployed. I'd probably be in a gutter, homeless. So thanks, the program. Anyway, to the talk, I'm talking about nature's fuel treatment, wildland fire. Carol alluded to it a little bit earlier. I'm talking about fire-on-fire interactions. What happens when a fire hits a past fire, or how do past fires influence subsequent fires? So basically, this whole thing is part of a joint fire science program project called Quantifying the Effectiveness and Longevity of Wildland Fire as a Fuel Treatment. And in this project, we looked at how fire influenced subsequent fire occurrence, subsequent fire size, and subsequent fire severity. In this talk, I'm only going to be talking about fire occurrence and fire size and how that's influenced by these previous fires. I will say that Vita and Corey Guker at the Northern Fire Science Network just wrote up a research brief about this whole JFSP-funded project. There's some copies of it in the back. So if you want to get more information in a condensed form, it's 2 to 3 pages, please check that out. It's also online. So, we've seen here in the whole puzzle piece of all these pictures and what have you that time since fire is really important. You could see on this map that when fires are occurring in a short interval, there's more of a puzzle piece. Fires are limiting subsequent fire spread. But at these longer time periods, there's fires that are kind of starting to burn over each other and reburn second entry and third entries. That has been brought up a lot here. So we expect time since fire to be extremely important. We also expect weather to be super important, right? The more extreme weather, the more likely that, so we theorized that fires are going to, basically extreme weather can override the influence of these previous fires in influencing subsequent fire. So we conducted a study looking at these various fire-on-fire interactions in these four wilderness study areas across Western North America. The crown of the continent ecosystem is what we're all here for. That's, you can see it there on the map, the CCE. That includes Glacier National Park and the whole Bob Marshall Wilderness Complex. But we also analyze fires and data from the Selway Bitterroot Wilderness, which, Stu was instrumental in promoting fire there, or the fire program, and the Frank Church as well, and then also down in the southwest, we have the Gila and Aldo Leopold. So I'm going to show results from all these study areas, but I think the crown of the continent is why we're here, and in these data right here. So when I say that fire limits subsequent fire occurrence, what we theorized here anyway is that fires were less likely to occur basically in areas that have recently burned compared to areas that are older fires or haven't burned within our record, So in this terminology or in this context, a fire occurrence is an ignition that results in a fire at least 50 acres in size. So a burning snag is not part of this analysis. So again, so we think that fires are going to be more likely to occur in areas that haven't burned or areas of these older fires. So we included ignitions and fires from 1972 to 2012. We have gone through and used satellite data to measure the perimeters of all fires from 1972, which is kind of the beginning of the Landsat record. And we're updating it now through 2012. I do want to say that there's this fire history here. Here's another one available that does use satellite data back to 1972 and also includes fire severity. I'm not showing any of the fire severity stuff here, but it is available in case you want it. So I'm gonna gloss over a lot of the stats, the statistical, mumbo jumbo. But basically, what we did is we basically looked at the observed ignitions, which are these. Oops, I thought that was an arrow. There we go. The observed ignitions are all these dots over here, and we compared the elapsed time between an observed ignition and a previous fire, or so, the elapsed time between a fire and a subsequent ignition, and compared that to randomly placed ignitions. And so what you expect, or what we expected, is that real ignitions, the length of time between a fire and a subsequent ignition would be longer on average than these random ignitions. So a random ignition, you're going to have a lot of ignitions that fall within fires that are 1 year old and 2 year old, 3 years old and 4 years old, and what have you. So again, that's our expectation. Real ignitions, the time between fire and a subsequent ignitions will be much longer on average than that of a real fire and a randomly placed ignition. And we use something called failure time analysis or survival analysis to analyze this. And I don't want to get too much into it, but basically what we'd expect is that this probability of failure is going to be higher for random ignitions than observed ignitions. And again, what that just means, if the probability of failure is higher, is that the length of time between a fire and a subsequent ignition is shorter. So basically, okay. So here's what we see. So this is the failure function, which is what we expected here, random versus observed. We see that in the data. This is for the Frank Church study area, by the way. We see that the black line is the random and the red line is the real. So the black line is what we'd observe, what we'd expect by chance, or is our null model, compared to the red line, which is our observed. So the probability of failure is much higher with the blue line than the red line. That means the length of time between a fire and a subsequent random ignition was shorter on average than that between the length of time between a fire and a real ignition. And so basically, when you run some other math on this and you get these things called the hazard function, as long as the black line is above the red line, it means that fire is indeed limiting subsequent fire occurrence. When those two lines cross, it means that fire is no longer limiting subsequent fire occurrence. So we have time since fire on this axis down here on the x-axis. And so in this study area, the Frank Church, the effect lasts over 25 years. So fire is limiting the occurrence of subsequent fire for over 25 years in the Frank Church. It's not that way everywhere, as you'll see here. So again, there's the Frank Church. Here's our area, the crown of the continent. You can see the black line and the red line cross at 21 years. So we'd say that fire limits subsequent fire occurrence for 21 years in the crown of the continent. There's a lot of uncertainty in that particular estimate. We had the least number of fire ignitions and fires here compared to some of the other study areas. But just so you can see some of the estimates from the other study areas, the Selway Bitterroot here, and on the bottom right, the Gila and Aldo Leopold, you see the differences. The next one I want to talk about very quickly is how wildland fire limits subsequent fire size. And basically, you see this puzzle piece effect up here. So you have a 2000 wildfire. This 2003 wildfire appears to be limited in size or extent by that previous 2000 fire. But however, this 1985 fire down here appears to not be limiting that 2003 fire. So that you see like this time since fire effect. And that's what I'm showing right there. So what we did is we basically, we defined fires that are either limit or do not limit subsequent fires, just a consistently based rule set. Blue equals yes, fire is being limited or is limiting subsequent fire spread or subsequent fire size. And then red says no, fire is not limiting subsequent fire. And when it's all said and done, is that we threw this all into a model, basically. And what this axis here shows is the probability that fire limits subsequent fire size. And over here is time since fire. So the crown of the continent is the black line. So very, young fires have a very high probability of limiting subsequent fire size. And as fire age increases, basically fires are less likely to limit. And you see that qualitatively here for sure. And now this allows us to give a more quantitative estimate. So it lasts about 17 years in the crown of the continent. You can see the blue line is our outlier, not outlier, it's the Gila and Aldo. That's a much higher fire frequency, warmer ponderosa pine dominated forest. That's totally what we'd expect. Extreme weather. Let's talk about that real quickly. I don't have much time. Basically, how does extreme weather influence this? We did a lot of, we basically figured out the day of burning for all the fires. We figured out the ERC. If you know the day of burning, you can know the ERC using weather station data or RAWS. And what you see, basically, here's the crown of the continent. The 99th percentile ERC is the red line. It dives a lot quicker. So the ability of fire to limit subsequent fire size is severely diminished under these extreme weather conditions. The black line over here shows the 50th percentile ERC. So you can see that fire limit subsequent fire spread more effectively or whatever under these moderate weather conditions compared to these extreme weather conditions. Something, again, we expect and we know it from our experience and qualitatively, but this is some good quantitative evidence of that occurring. So basically, yes, fire limit subsequent fire occurrence, yes, fire limit subsequent fire size, and the effect diminishes with time since fire, diminishes with extreme weather. And we are continuing to work on this. We have other aspects we're working on, other components we are currently working on. I'm not going to get too much into it. There's a pretty graph that I'm not going to explain.
So they can eat.
Yeah, so you can eat. I've got a lot of friends and collaborators that have helped out with these projects. And I just want to really emphasize here at the end that this is a very important program. So to the people coming up through the ranks of the Forest Service, let's keep it going, keep it going. So.
I got a question.
Go ahead, Dave.
Sean, one of the things I'm thinking about is in your data set, you show in some instances where the second entry of fire into a previous fire, can't remember now exactly the term that you used, but I think one of the things that you might need to look at is the intensity of the fire and effects of that second entry. Where the initial entry most likely in these larger fires is basically a stand replacement type of intensity, where the second entry, even though it's over 15 or 20 years, may be much more of a moderate to lower intensity backing fire or ground fire that does not take out any residual or a small percentage of residual overstory.
Yeah, exactly. That's a great point. And that's actually another component of the study that I didn't show that was part of the overall JFSP. And so the results are summarized in that research brief, and I could talk about that to you later. But yeah, we did look at severity as measured by satellite data and how it differed between first entry and second entry.